So first of all, I think it was great that most of you, maybe I should have said that before, but that most of you, run the tool and was able to follow the explanations by Carlos. I think they were quite good and detailed, but of course, please feel free again to just reach out to us if you have any other questions, or if you are planning to maybe use FlexTool in some of your projects, or even some sort of support. So starting with these with this next session, so if we go to the different ways of providing flexibility in our system, of course, first we have flexibility from generation, which has to do with the characteristics of these technologies like ramping, startup times, all well known and possible to be captured in the model. In particular, as we go to shorter time resolutions, and then when moving power, I saw that some of you mentioned distribution. We do not go in the granularity of distribution, but typically we stay at the system level, meaning we only model the transmission network. To go to the distribution, probably you would need a grid integration study, something that we have a team in IRENA also doing that, but we don't typically go with that when we do a flexibility assessment. These are, let's say, two different products that sometimes, of course, depending on the project, we can merge them together, or but these are somehow different. And then if we are talking about generation and then transmission, I would say these are typically comprise what could be called flexibility resources in today's power systems. But then as we go to the transition, we will start seeing, of course, more and more assets in the short and medium term, such as storage, demand response, sector coupling. Most of these, as you know, are already a reality in some countries or regions, but we still need to significantly scale up all of them to achieve net zero by 2050 or 2060 and so on. So in this session, again, we are going to show you how we typically represent some of them in the FlexTool. Again, any comments that you may have about the modeling, again, they are all welcome, and maybe possibly we can improve them, or we can include them actually in the next version of the tool. So first, storage. Just to start, we launched the electricity storage evaluation framework earlier this year, which brings an overview to policymakers on how to monetize and set up a project. And then in this report, in particular in the part 2 of this report, you can find it in our website, of course. We try to represent how we can use models to prepare a flexibility analysis that includes a setup that recognizes the value of storage. So if we go through this 5-stage process that you can see on the screen, we start with identifying the services that storage can provide to integrate renewables under a specific country or energy context. Then in a second step, we try to match the services with the wide range of storage technologies, or a sort of mapping of suitable technologies. And then in phase 3, we precisely use a capacity expansion model that can be used to capture the value of storage and the respective capacity that would be required or could possibly be required in your system, of course, compared to all other flexible alternatives. And afterwards, or jointly, we can also use a dispatch model to optimize operation and capture the multiple stacked benefits of storage. And finally, the last phase would be at the project level already. For instance, there may be a case where the benefits to the system of a specific storage project exceeds costs, but then the project revenues themselves are still not enough to cover these costs. So these two ideally should converge. So that's what we try to bring with this report. So, going to FlexTool already. So storage is defined just as any other technology in our model in the unit type spreadsheet. Of course, with the difference that some of the characteristics that apply to the storage obviously do not apply to generation technologies or some of the generation technologies and vice versa. So some of these fields are charging and discharging efficiency that can be, of course, different. There is also the possibility of defining a self discharge loss, which is that loss that you have even when the battery is not under operation, which may have to do with the aging of the battery, but in general, most of the storage chemical technologies will likely actually suffer with that, in particular at high temperature environments. Then there are naturally separate fields to define the power capacity in megawatts and then the energy capacity in megawatt hours. And especially for pumped storage, it may be important also to set storage levels at the beginning and at the end of our simulation. So, and this feature, by the way, as you may suspect, also applies to conventional hydropower plants. So you can also, in conventional reservoirs, let's say, you can also, of course, set start and end levels for storage. And finally, if there is a natural water inflow coming into the pump storage upper reservoir, that can also be naturally modeled. And then in addition, in the technologies field, we have two options to set power to energy ratios. That can be either fixed. So if we are already modeling a specific technology that we already have in mind, so we can already set this value in the model. So that would mean, for instance, if we have an 1 hour ratio, that would mean 1 megawatt power rating, and then of course 1 megawatt hour energy rating. But we can also set the model to freely optimize power and energy separately. So the model can tell us if we are, let's say, in need of energy or power. And then from the results itself, we can try to understand which among the available technologies, there are many, right, would translate to that particular value. So this has to do, of course, that different end users call for different technologies or different energy to power ratios. And again, so that leads to different technologies. So for instance, if we are talking about frequency regulation, that will likely require a high or a higher power rating. While if we are talking about a system backup, going to adequacy, then we should probably favor better energy ratings. And typically batteries are designed to maximize performance in one or another. So hydrogen, then going to hydrogen. So hydrogen has been considered by countries a key component towards a net zero. And therefore a topic often seen in the agenda of members, though sometimes with different perspectives. And one of the main reasons for that is that it allows renewable power to be used into sectors such as transport, industry, and building. So adding on to electrification, we can also, with the use of green hydrogen, we can also have a sort of indirect electrification. And of course, in addition to replacing the existing hydrogen demand, which is currently met by natural gas and coal-based hydrogen, mainly for ammonia production and to increase the quality of oil subproducts. Of course, that can be also replaced with green hydrogen. So when modeling it in FlexTool, it starts from this yellow area that you can see on the left with power generation. Then, of course, we need to add an electrolyzer, which uses this power to split water into hydrogen and oxygen. And then this hydrogen can meet the hydrogen demand itself that of course, we set in our model. And that may take then many different routes all the way until end users. And finally, it could also be used to produce power back to the grid under specific cases with the use of fuel cells or gas turbines. Having in mind that, of course, producing power, then hydrogen and back to power has an overall low efficiency. So that should be relevant in particular for that last mile going towards 80 or 100% renewable systems. And finally, some of these ideas can be seen in the many reports that you can see on the right that we have produced on the topic of hydrogen and broader on its role in the energy transition. So in FlexTool, so how we represent hydrogen in FlexTool? First, we need, of course, to create a demand profile for hydrogen, same way that, or very similar the way we do for instance, for demand for power. This demand will be met either by green hydrogen or even by hydrogen made from fossil fuels, if we also want to represent them in our model. And then in parallel, we need to create a hydrogen grid where producers or the units in our system that are producing sorry, it looked that I had some disconnection here, but I think it's still working, right?
Yes.
Okay, sorry, something just popped up here on my screen. Okay, sorry about that. So so again, sorry. So maybe just quickly back. So of course we need to set our demand profile for hydrogen, and then in parallel we need to create a hydrogen grid where our sets, or not sets, or our assets in our system that produce hydrogen will also be connected to. For green hydrogen, again, of course, we need to define an electrolyzer unit which will consume power and produce hydrogen into the grid, into the hydrogen grid, looking in particular for periods of lower electricity price. And then the grid can also include storage, meaning that consumption doesn't need necessarily to take place at the same time of production. And finally, sorry, just. And finally, we may also want to add a fuel cell again, or a gas turbine that would be used to produce a power back to the grid. So we can naturally define the efficiencies of each step of this process. Again, parameters are defined on our technology spreadsheet. To some extent similar to those of generic power plants. So again, efficiency, we can add power ramps, lifetime, and some other parameters that apply to an electrolyzer. By the way, we launched recently a report specifically about electrolyzers. So how to scale them and reduce costs, and where you can also find some useful parameters that can be useful for you for your modeling. It is one of those covers of hydrogen reports in the beginning, if I'm not mistaken, the lower left one, I think. Anyway, you can see it there. So we finally model our system in a way that we have the two grids connected, representing the sector coupling, right? We have the power grid, and then we have the hydrogen grid or a gas grid. We can also do it, of course, we could also do it for natural gas and then have some adjustment. We could even have for natural gas and then for hydrogen, and also have some adjustments between them. So again, we have power from renewables going to the hydrogen grid and eventually back to the power grid with electrolyzers. Sorry, with electrolyzers in the first step, and then of course fuel cell or gas turbines, and also with the option of modeling blue hydrogen, so hydrogen from natural gas or coal with CCS. Of course, we can also model without CCS, but then if we're going towards energy or decarbonization scenarios, we are likely willing to model it with blue hydrogen at least. Yeah. So yeah, so I think that was yeah, all from my side. With this, I would just hand it over to Carlos to complete the remaining part. Maybe I can just again. Okay, you can.
Yep.
Okay. Yeah. Okay.
Thank you very much.
Yeah.
Raul. I think that was very comprehensive and very useful. So I will be explaining now the other flexibility options, including power to heat, power to hydrogen, demand response, etc. So the next flexibility option is power to heat. Power to heat is very similar to what Raul has explained about power to hydrogen. It's basically about defining a new grid that is not electricity. You call that grid heat, or the name, whatever name you want. And the structure is the same. So I was thinking that instead of going through the slides, because they are very similar, I will show this in FlexTool. We won't simulate anything, but just to show it in the input file. So basically, I'm in the template input file. In the template input file, you can probably see that we don't only have electricity grid. You can see here clearly that we have also the heat grid, and with a node called heat A. And here we define a demand. In this case, it will be a heat demand and the other parameters. So that's how we define the heat node. Then if we go to unit type, we can see here, for example, that we have defined a unit that is called a heat pump. And instead of defining an efficiency, what we do is we define a conversion efficiency. The difference between efficiency and a conversion efficiency is those units that generate energy for the specific grid. So for example, a power plant generates energy for the electricity grid. So we use the parameter efficiency. A natural gas boiler, for example, generates heat for the heat grid. So we would define efficiency in that case, and we will assign natural gas as a fuel for that. In this case, we define conversion efficiency because this is a device that takes electricity from the electricity grid and converts this to heat in the heat grid. So it sends somehow energy from one grid in my model from another grid in our model. That's why we use the conversion efficiency parameter. In this case, it's defined as 4 because this will be the coefficient of performance. So the heat pump will produce 4 units of heat per 1 of electricity. This is the case also for electrolyzers, and an electrolyzer is taking electricity from the electricity grid in our model, converting it to hydrogen for the hydrogen grid in our model. So in that case, it's conversion efficiency. If we are using a steam methane reforming, then it will be efficiency because we're using natural gas as a fuel, and it will be a unit in that grid. So that's how we define it, and then we just have to go to units. And in units, the only specificity in this case is that instead of only defining output grid and output nodes, we also have to define input grid and input node, which is where the energy is coming from. In this case, it comes from electricity grid node A, and it goes to heat grid node heat A. And the rest is the same. We define the capacity of the heat pump, and it's pretty much the same. So with that, we have a heat pump that supplies my electricity grid. This will be the same with hydrogen, or this will be the same with any other commodity that we want to model and goes from one energy grid to another. And actually, this opens a big variety of possibilities with the tool, no? Because you can even have a gas grid that converts. So, for example, you can have a hydrogen grid that then converts this hydrogen into ammonia by some efficiency and some process, or it converts this hydrogen to methane, etc. So there's a lot of possibilities once you understand what's the concept behind sector coupling in FlexTool. So going back to the slide deck, we have power to heat. I have pretty much explained this. We have the electricity grid. There's some device like a heat pump that converts electricity to other energy carrier, in this case heat. And the rest, it's the same as hydrogen. We define a heat demand in TS energy, like in electricity, just assigning it to the heat node. We can define a storage. In this case, will be a thermal storage, the same way as we do for electricity. Usually here we will use the property self-discharge loss, because that's very relevant in thermal storage. And we can use direct heat devices like a natural gas boiler or a solar thermal boiler. This I already have explained. The only added thing here is that we have the options in FlexTool to define a dynamic efficiency of heat pumps. So we can add a time series of the efficiency of the heat pump that is based on the outside temperature. And this is very important because the efficiency in a heat pump varies depending on the temperature, I think also on the loads, but at least we can kind of represent this somehow. And then also on the heat part, we have the advanced modeling of CHP units. This I have already showed this before, but basically we can have we can model CHP units with one fuel input and two outputs, and in a way that both outputs depends on each other. So we have modeled some inequality and equality constraints that represents the relationship between heat and electricity outputs and how one varies when the other also varies. Then on electric vehicles, it's the same concept as power to heat and power to hydrogen. But there are different ways actually of modeling electric vehicles. The most simple way is to model EVs as a predefined demand, so that we will add it to our demand profile, and that's it. We have modeled EVs. This will be the most simplest way, but there's nothing advanced in here. And then we have the most advanced way, which is how to model vehicle to grids in as I said, it's very similar to power to heat and power to hydrogen. In this case, we will have some demands defined in what we will call the electromobility grid. So we have the heat grid, a hydrogen grid, and we have an electromobility grid. We have a demand which represents the demand of electric vehicles. So it's basically what they consume by using the vehicle for mobility reasons. And then we have a device that we call, for example, EV charger, which is another conversion unit. No, it's like the heat pump that gets electricity from the electricity grid and sends this electricity with some efficiency to the electromobility grid to charge the vehicle. And we can have another device that does the other way around. It gets electricity from the electric vehicle, and it sends this electricity to the electricity grid, which can be the V2G charger. And with this, we can somehow also model electric vehicles, either smart charging or with vehicle to grid. In the folder, in the input data folder, there's a file called templates EVs. So this one. And here, if you have interest on this, you can actually check how to do this in FlexTool. So we don't go deep on this because we don't really have time to explain all this, but we are thinking in the future to do a more advanced training in the tool for all regions. We've been doing this more basic training. Okay, so this was EVs. Well, we have here transmission, but we've already seen how to model transmission in the demo model 1, so there's not much to say in here. The only thing is, well, this is already for very advanced users of the tool in case there's something strange. But basically, since the model is linear and we are modeling losses, we need two variables to model losses. And the problem with this is that losses in the model, in a linear model, can be used to make a model leak, which means that I can be sending energy from node A to node B and back from node B to node A, and somehow willing, so avoiding some of the costs of from the objective function by doing this, and this energy will go nowhere. But anyway, as I said, this is probably not very relevant today. Then for demand response, well, you can see here that we published a couple of years ago this work on demand side flexibility for power sector transformation, where we map that demand side flexibility can come from power to heat, power to hydrogen, EVs, smart appliances, or industrial processes. So this is just in case you are interested on demand side flexibility, in case you want to take a look. But on FlexTool, demand response, we usually model it as a generator that can sell or that can that can generate or that can absorb energy. And what we do is, in order to model an increase in demand, we use a generator with negative price and empty charging efficiency. And in case we want demand response downwards, we model a generator with a positive price and efficiency. And then in units, for demand increase, the capacity is negative. For demand decrease, the capacity is positive, because at the end is like a generator. And with this, actually, we finished the material we had for today. I would say, as the next steps, as usual, will be to plan an advanced training. But as I said, we are planning to do this for all the regions. We have been doing this more basic training. I also mentioned that this training was done with IRENA FlexTool 2.0. We are currently developing IRENA FlexTool 3.0. It's not yet even in beta version, but the plan is to launch it by the end of the year, end of next year. The input data file in principle will not change a lot. The interface will change, and there will be some other changes, like migrating it to Python. But by next year, we probably will be doing more trainings. Apart from this, yeah, I would like also to open the floor for questions and answers that there might be in the panel. But I don't see. Well, I see Manuel. Yeah.
Yes, I can always ask a question. You showed the demand response modeled as a generator, but will this demand response also be, let's say, if demand is reduced, will it be increased later on, or would then this be modeled like some storage device? And if so, how to limit this time frame? Let's say if a certain demand can be met 1 or 2 hours later, or is it really more as a kind of reserve to the system for some instantaneous flexibility?
Yeah, in that case, what we have presented, it's instantaneous for a specific moment in the system. But it's true that normally some devices can shift demand downwards for 4 hours and then upwards in 4 hours. No. In that case, what I will do is model this as a storage. So same as a battery with capacity of the battery being the power multiplied by 4, and that's it. That's the best we can do, I think. Well, I see in the chat someone mentioning if we could share a document showing the equations used in the model. We have time, so I can show this, but basically in the IRENA website we have a publication called Power System Flexibility for the Energy Transition, the part 2 specifically. I don't know, Raul, if you can share that link. But apart from this, there's a possibility for more advanced users to go to the source code, so the mathematical model directly from FlexTool.
Just quickly, sorry, the link is already, I already shared this in the chat, because there was a question about benchmarking, so it's precisely that same report.
Okay, yeah, thank you. Yes, I just saw it. So that's the link before in the chat to the publication. But as I was mentioning, in case someone has interest on checking the source code of the tool, the mathematical model is in MathProc. It's this file here called flexmodel.mod. So if you open this with some editor, like I have Notepad++, for example, you can access the source code. The tool is open source, so you can do with this whatever you want, basically. But here you can see the sets. If you have ever used GAMS or some other mathematical models, all the parameters, and then if you scroll down, you can see all the equations. Yeah, once you have experience with the tool, this file is actually important to check in which equation there's an error. Maybe another thing that might be important before finishing, in case you keep using the tool. So you will see that when you run simulations, a results file folder is generated. So if you come to this results folder, you can see the scenarios that you have run. So you enter this folder with the different scenarios. We can check base, for example. And there will be a lot of Excel files. But most importantly, there will be 3 text files called outputs, the 1, output 2, and output 3. And these are important because it's the commands, the command lines from the simulation. So in this case, everything went well, so we cannot really check any error. But sometimes if the model starts simulating and all of a sudden it stops or there's an error, you can usually check here where the error was. But as I said, this is already more advanced, but in case you keep using the tool, it's something you will need at some point. And I think that's pretty much it. I don't have many more for today. I also don't see more questions. As I said, if you keep using the tool and you have doubts on how to do some things or there's some error, just feel free to contact us. You also have the FlexTool support email in case you have any doubts. And from my side, I will conclude the training. I don't know if Raul or Manuel would like to say anything else.
Yeah, thank you. Many thanks, Carlos. Maybe just quickly, also as you have this folder open, I'm not sure if it would be worth also to show that parameters folder, or maybe they are basically they have the same information of the output the files, right? In case of errors as well, that a place that sometimes you can also spot them.
In the param.
But typically, when you run the model, if you get an error, but typically a window, of course, will pop up with a sort of a code. Yeah. Most of the time, you can already know, because of course it will mention, for instance, fuel that is out of domain or something like that. For instance, there was a question regarding fuels. If we change the name, what would happen? So sometimes you can really, quickly spot it, but sometimes you will be a bit in a doubt. So you can go either to that file that Carlos mentioned, or the parameters folder. Sometimes you may also have some clues there.
Yeah, in the parameter file.
Yeah.
But yeah, the output will point you to which file. Yeah.
Yeah. Okay. Then great. Then I think that was just a quick comment. Yeah. So from my side, I think that's all as well. I think Carlos already mentioned everything. So please feel free to reach out to us if you have any questions, or if there would be anything from our side. Maybe also reminding that there are some training materials in our website. So, or maybe let me also put my video. Sorry. So there are some training materials in our website. So some slides and some other documents. In addition to both the flexibility report part 1 and part 2. Mainly, the part 1 actually is a bit more about the flexibility concept in general. So it's something that more general about flexibility. But then the part 2, which is that one that I shared the link, you can also find some additional aspects and information and guidelines about the tool itself. So I think that would be all. I hope that was useful for you yesterday and also today. And have a nice day, from my side. So please, and then I hand it over to Manuel for his final words as well. Thank you.
No, thank you very much, Raul. Thank you very much, Carlos. And really just to thank you for being there with us to organize this event back to back to our ongoing workshop. I'm sure it's much appreciated by the participants to have this opportunity to get some experience in a freely available open source tool that, as we have heard in the presentation in the morning session from Andre, it takes basically a couple of hours or days to get set up, maybe at least a first simple case. And I think that's really valuable. Thank you very